started giving different results and still do, and cosmologists have no idea why. The James Webb Space Telescope, with its recent discoveries, has worsened the crisis even more. We've made a video about the crisis in cosmology, and you can click on the link in the description to watch it. But for now, here's a very quick refresher. The universe is expanding, and distant galaxies are moving farther away from us. When we calculate the rate of the expansion of the universe using the cosmic microwave background, which is the light left over from when the universe was only 380,000 years old, this is what we get. Then there's another method where we know how bright distant supernovas are supposed to be, and we can compare that to how bright they appear when we measure them. We can then use that information to estimate the expansion rate of the universe at the time of the supernova. When we calculate the expansion rate using this method, also called standard candles, this is what we get. So, the expansion rate of the universe is called the Hubble constant. However, the difference between the result of the two methods is called the Hubble tension. And this, my friends, is the crisis in cosmology. But this is not the only crisis anymore. A recent cosmological distress has emerged, challenging our models like never before. I spent all my life developing a particular theory of the universe, and now that theory is being questioned. I welcome that because that's how we move forward, that's how we make progress in science, welcomes Dr. Martin Fee of the European Space Agency. Welcome to territory. This is your space. When you look up in the sky, given you are not in a city or place obstructing starlight, you see countless stars. You also see the Andromeda galaxy as a smudge amidst the many stars. That's because the universe is filled with stars and galaxies. The question is, how much of the universe do they fill? In other words, how much matter is actually there? A simple question, the answer to which is anything but simple. This dilemma exists largely because current cosmological observations simply disagree on how matter is distributed in the present-day universe. And this has given rise to the mysterious S8 tension, aka the new cosmological distress. Now, the S8 tension is a measure of the lumpiness or clustering of matter in the universe. To put it simply, picture the universe as this colossal puzzle where the pieces of matter are scattered throughout space. Scientists want to understand how this matter is distributed and how it clumps together. There are two ways to measure it. First, by precisely calculating it using low redshift observations, such as weak gravitational lensing. Gravitational lensing is a phenomenon where the immense gravitational pull of massive objects like black holes and galaxies acts as cosmic magnifying glasses, bending and distorting the light from more distant objects that would otherwise be invisible, providing unique insights into the vast universe. However, the S8 value derived from the second method, which is the standard model of cosmology based on cosmic microwave background measurements, does not align with values obtained from low redshift observations. This discrepancy forms the perplexing heart of the S8 tension. Now, what do we do? Clearly, there is something that we do not understand at all, something that isn't quite adding up. Despite the countless theories and observations and hypothetical entities supporting those theories, what is going on? To find out, astronomers used one of the most powerful supercomputers in the world to carry out the largest cosmological simulations ever. One cannot even fathom the scale of this project until you realize that the simulations required a total of more than 50 million hours of computer time distributed over the 30,000 processors that make up the Dracosmo J supercomputer at Durham University in the UK. The project is called Flamingo, a convoluted acronym of Full Hydro Large-Scale Structure Simulations with All-Sky Mapping for the interpretation of next-generation observations. Apart from its huge size and high resolution, Flamingo sets itself apart from earlier simulations by incorporating much more than gravity alone. Up to now, most of the cosmological computational simulations of our universe focused on modeling dark matter only, as it is the main matter component. However, even though normal baryonic matter makes up only 1/5 of all the mass in the universe, it can have a big effect on how cosmic matter is distributed at small distances. For instance, galactic winds powered by supermassive black holes and supernova explosions may stall the growth of galaxies. And unlike previous simulations that only consider dark matter, Flamingo takes into account and tracks ordinary matter too, because although dark matter dominates gravity, the contribution of ordinary matter can no longer be neglected. While the simulation marks significant progress, like accurately matching the formation of the Milky Way and the Andromeda Galaxy, amongst many others, it fell short of explaining the observed weak clumping of matter in the present-day universe. In other words, it failed to resolve the very thing it was created to help solve, the S8 tension. Or might I say that the Flamingo simulations may be indicating that something is terribly wrong with our cherished standard model of cosmology. The simulation also contradicts the observations of the James Webb Space Telescope and other observatories about the distribution of matter in the universe. The current theory beautifully explains how galaxies evolved. But there's a problem. It predicts that they are 7% more closely clustered together than they actually are. The new computer simulation is much more detailed and takes into account the role of supermassive black holes. But that's not right either. It's still 5% more clumpy. Recent observations from Webb have proved that the Hubble tension actually exists. That's right. The James Webb Space Telescope has cross-verified the findings of its predecessor, the Hubble Space Telescope. The pioneering observatory discovered that Hubble's calculations of the universe's expansion rate are exceptional, intensifying the so-called Hubble tension. In essence, measurements of the universe's expansion rate defined by the Hubble constant simply do not align. Nobody knows what is causing it, but some hypotheses call for new physics to explain the apparent contradiction. With measurement errors ruled out, what remains is the intriguing and exhilarating possibility that we have misconceived the nature of the universe. New theories are already making their way into the limelight, with some calling for the removal of dark matter. What do you guys think? Drop in your comments to let me know. And don't forget to subscribe to Territory because this is your space. Certainly, here's more detailed information about cosmology, including the Hubble tension, cosmological simulations, the James Webb Space Telescope, and challenges to the standard model of cosmology. Cosmology, the study of the origin, evolution, and structure of the universe, has been a fascinating and challenging field for scientists and researchers. One of the key mysteries in cosmology is the Hubble tension, which refers to the discrepancy in measurement of the universe's expansion rate using different methods. This tension has sparked intense debate and prompted groundbreaking research to unravel its underlying causes. The Hubble tension arises from two main methods of measuring the universe's expansion rate, also known as the Hubble constant. The first method relies on observations of the cosmic microwave background, CMB, which is the leftover radiation from the early universe. By analyzing the fluctuations in the CMB, scientists can infer the rate of cosmic expansion at that time. However, this method yields a slightly different value for the Hubble constant compared to the second method. The second method involves using distant supernovae as standard candles to measure cosmic distances and infer the expansion rate of the universe. This approach, pioneered by the Hubble Space Telescope and refined by subsequent observations, provides another estimate of the Hubble constant. Surprisingly, the results from these two methods do not align, leading to the Hubble tension. The implications of the Hubble tension are profound, as they challenge the validity of our current understanding of cosmology. If the discrepancies persist, it could indicate the presence of unknown physical processes or even the need for a new model of the universe. This uncertainty has fueled intense scientific scrutiny and efforts to reconcile the conflicting measurements. To address the Hubble tension and explore the underlying dynamics of the universe, scientists have turned to cosmological simulations. These simulations use advanced computational models to recreate the evolution of the universe, incorporating factors such as dark matter, ordinary matter, dark energy, and gravitational interactions. One notable simulation project is Flamingo, full hydro large-scale structure simulations with all-sky mapping for the interpretation of next-generation observations, which represents a collaborative effort involving researchers from various institutions. Flamingo's goal is to simulate the large-scale structure of the universe and investigate how different factors contribute to cosmic evolution. The Flamingo simulations have provided valuable insights into the distribution of matter in the universe, the formation of galaxies and galaxy clusters, and the role of dark matter in shaping cosmic structures. However, like other simulations, Flamingo has encountered challenges in fully capturing the observed clumpiness of matter and reconciling it with observational data. One of the key challenges highlighted by Flamingo and other simulations is the discrepancy between predictions based on the standard model of cosmology and actual observations. For instance, the simulation suggests that galaxies should be more closely clustered together than observed, pointing to potential shortcomings in our current understanding of cosmic dynamics. The emergence of the James Webb Space Telescope, JWST, has added a new dimension to cosmological research. JWST, with its advanced capabilities and sensitivity, promises to provide unprecedented insights into distant galaxies, early cosmic epochs, and fundamental cosmological parameters. Recent observations from JWST have contributed to the ongoing debate about the Hubble tension. Initial data from JWST deep field surveys and spectroscopic analyses have hinted at potential discrepancies in cosmic distances and redshift measurements, further complicating the picture of cosmic expansion. The confluence of observational data, computational simulations, and theoretical models underscores the complexity of cosmology and the need for interdisciplinary collaboration. Scientists across multiple disciplines, from astrophysics to computational science, are working together to unravel the mysteries of the universe and refine our understanding of its fundamental properties. In conclusion, cosmology remains a dynamic and evolving field driven by curiosity, innovation, and the quest for deeper knowledge. The challenges posed by the Hubble tension, cosmological simulations, and advanced observatories like JWST propel us toward a more comprehensive and nuanced understanding of the cosmos, pushing the boundaries of human inquiry and scientific discovery. Thank you for watching. These stars and their physics and movement mirror are those of the stars that birthed them. Despite their immense gravitational pull, black holes continue to capture our attention. The detection of neutron star collisions by gravitational wave detectors such as LIGO and Virgo may shed light on the existence of some smaller black holes. However, the likelihood of a black hole colliding with Earth is incredibly low, estimated at only 1 in 40 billion throughout Earth's history. These odds increase over time to about 1 in 10 to the power of 20, comparable to winning the lottery jackpot 3 times consecutively. Collisions are not the sole concern with black holes. Their gravitational effects can cause significant disruption. Proximity to a black hole could disrupt your orbit or worse, lead to consumption by the black hole. The tidal forces of a black hole can rip a planet apart, leaving only spaghetti-like remnants. However, this scenario is rare and would occur if a black hole came very close to Earth, within about 10 astronomical units, an event expected once every 400 million years. Even if a supermassive black hole approached Earth, it would take millions of years to reach us, providing ample time for preparation. As it drew near, it would appear as a distant point of light to a star in the sky. Its gravitational impact on Earth would be minimal, as black holes do not emit harmful light or radiation. If a supermassive black hole neared Earth, it could create gravitational lensing, distorting light from objects behind it and causing a cosmic optical illusion that warps background object shapes. Additionally, the black hole might induce microlensing, temporarily amplifying the light from background stars and creating a bright phenomenon.